Back. This is our first video on vectors. It will cover most of the material in chapter 10, section 4, and it pretty much goes by the textbook. So here we go. Let's see how this works. I'm projecting off of a PowerPoint presentation. I thought this might be a little better than me writing on the whiteboard. We'll see how it works out. This is key to vector operations 1, which I have on Blackboard for you, and I recommend that you print it out. You can follow along. So if you want to pause the video, get out a pen or pencil, because sometimes the computations, not every step is shown on this presentation. So here we go, Vector Operations 1, Section 10.4. Okay, here we go. First idea is the idea of a position vector. And a position vector is a vector that has its tail at the origin. So what's pictured is vector V, which has its tail at O. It has its head at point P. And if we counted, you have A units here and B units here, and that's how we would symbolize it. Okay, moving along. So what we have here is position vector V. We have another vector V here. Now these vectors, and first of all a vector is it's an arrow. It could be in 2 dimensions, it could be in space. In our textbook, we're going to stick to 2 dimensions. But 2 vectors are equal if they have the same length, okay, and the same tilt if they're parallel. Okay, so these vectors are actually equal. So for purposes of computation, understanding, what we typically do is we take vectors and we put them with the tail at the origin. So I'm going to call those position vectors. So the formula is simply, yes, change in, an X here and a change in Y. So all we do is count, and that's how it's done. Very simple. Let's do an example. Graphing and writing position vectors. All right, let's suppose point P1 is -1, 2, point P2 is 4, 6, and we want to graph the vector, this time W, and we typically symbolize vectors with boldface print if we can. Okay, so if we're going from P1 to P2, notice the direction of the arrow here, that the tail is at P1 and the head is at P2. So this says find the position vector V equal to vector W. Okay, so notice that this doesn't start at the origin. So what we do, we simply look at the little picture here, diagram, and here's P1, here's P2, and we simply count. 1, 2, 3, 4, 5. We're going 5 over. That's our X. And 1, 2, 3, 4 up. So this would be equivalent to the position vector 5, 4. Notice it starts at the origin. Okay, position vector V has its tail at the origin. And this is the computation we talked about. So it's very easy counting boxes. Okay, moving along. These vectors are equal vectors. Okay, they have different names, but they're equal vectors. In each case, we go 1, 2, 3, 4 over and 3 up in each case. So these are equivalent to the vector 4, 3. Okay, now notice the angle brackets here. This is how we distinguish between a vector and a point. Okay, so this would be, these are the position vectors equivalent to 4, 3. Okay, adding vectors. Adding vectors, very easy. We go simply from head to tail. Okay, so vector V starts here, goes over 3, 4, and up 1. So vector V is 4, 1. Again, notice the use of the angle brackets. And vector W looks like it's 1, 2, 3 over and 3 up. So vector W is symbolized by 3, 3 angle brackets. And what could be easier, all right, to go from the tail of V to the head of W, All right, if you do a little count, you go 1, 2, 3, 4, 5, 6, 7, and up 4. And notice how simple this computation is. Okay, so head to tail, that's what we do. Okay, vector adding is commutative, and you can tell by this diagram that whether I start with the W first and then the V, or the V first and then the W, I end up at the same place. So V plus W, W plus V would be the position vector 6, 4. Okay, and don't forget, the purple W vector is equal to the blue vector W for the simple reason that they have the same, let's over 2 and up 3, they have the same position vectors. Okay? All right. Vector addition is also associative. The diagram is a little tricky. I'm going to leave it to you to just follow it along. As position vectors, that's always an easier way of looking at these things. Now U is over 2 and up 2, so U is the position vector 2, 2. V is the position vector we're going 4 to the right and down 2. So notice 4, negative 2. And W, of course, is the position vector here, which is 1, 2, 3, 4, and up 4. And it's very easy to show these computations come out to the same result. The vector in pink is 10, 4 with the angle brackets, vector notation. Okay, so what we want to do is we generally want to go into position vector format. Makes things a lot easier. Okay, scalar multiples. A scalar multiple is when you simply multiply the coordinates or the components of a vector. So V, as you can see, is 3, 2. And 2V, well, would be 6, 4. And if I count out, you can see that this vector has twice the length of this one, and yet they are parallel. So when we use scalar multiplication, we affect the magnitude or the length of the vector, but not its angle. Okay, and negative 1V, well, if V is 3, 2, then this would be negative 3, negative 2. So we start here, and we go back 3 down 2. That's the meaning of the negative. So we have the usual meaning of positive and negative orientation. Okay, graph the following vectors. Okay, so we're given U, V, and W, and we're asked to make the graphs. Okay, so let's go ahead and let's do that. And we're going to do this in 2 different ways. We're going to take a graphical approach, and then we're going to take a component by component algebraic approach. Okay, so here we go. Let's talk about V minus W. Okay, first of all, to get V minus W, I take V, tail to head, and I take tail to head of W, and I connect them. So if you go back to this picture, okay, here's V, and W would be 2, negative 2. So minus W would just be the opposite. Okay, so let's go ahead. Where am I now? I lose track of where I am. No. Yes, I did. Okay, so V minus W. This is V. This is minus W. And this would be V minus W. Notice that this is the tail. This is the head. Okay, so V minus W, 1 looks like 4. Okay. And you can do the same thing with the others, and I advise you to, count and try this a little bit. Okay, so we're looking for the combination 2V plus 3W. Okay, so if we go back, 2V would therefore be 6, 4. Okay, so 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, that would be 2V. And 3W, well, W is 2, negative 2, so 3W would be 6, negative 6. And as you can see, this would be our sum. Okay, this is a little more complicated. Take a look at it, plot them out, just count boxes. It's not hard. Okay, now we're going to do the same thing algebraically. And this time what we want to do is we want to realize that u is 1 comma 3 written as a position vector. Okay, so u 1 comma 3, v 3 comma 2, 3, 2, and w 2, negative 2 as we've shown. Okay, and again, notice the use of the angle brackets to indicate we're talking about vectors, in fact, position vectors. And now it's just a computational thing. V minus W, you can see it's component by component, 3 minus 2, and 2 minus a negative 2, and you can see our result. And the rest of these follow them. Very simple. It's surprisingly easy. So we have two different ways of doing this. We have components, which is an algebraic approach, and we have a visual or a graphical approach. Okay, now we have unit vectors I and j, also known as Kronecker vectors, named after a German mathematician named Kronecker. So a unit vector has length 1. A unit vector in the x direction is symbolized by I. A unit vector in the y direction is symbolized by j. It's alphabetical order, x, y, I, j. If we were talking about 3 dimensions, which I do have that on Blackboard, it would be I, j, k. Those are known as the Kronecker vectors. Okay, so this you can look at. I wouldn't worry about it. This is like the counting boxes method, but and with position vectors, and these are some basic rules, but I really don't want you to focus on these. I want you to just think about what's going on. The only new thing here is this. This is called the magnitude. The magnitude of a vector, as you can see, we just used the Pythagorean theorem, and let's see, this is the vector, this is the I component or the X component, this is the J component or the Y component. It simply is the Pythagorean theorem, okay? And, we can write it in this form as well. This is the IJ version or the Kronecker vector version. This is as a position vector. Really the same thing, and we're going to go back and forth between the two. Okay, again, we have some visual explanations here. I don't want you to worry about all the notation. Most of this is common sense. So let's not worry about this. You can go back and look at it later if you wish, but it is pretty much common sense. So moving along, let's do some examples. Using vector components, adding and subtracting examples. So vector V, we used to write this as 2 comma 3 with the angle brackets. That's equivalent completely to 2i plus 3j. Notice the I is the x position, and notice the j corresponds to the vertical or the y position. Vector W is a different vector, symbolized by 3i minus 4j, or position vector 3 comma negative 4. And what we're going to do is do the computations. And it's just adding component by component. So if we're going to add the I of the x components, v plus j is 5. And for the j components, you can see it's a negative 1. So it's pretty easy stuff. Now, this is how we're going to do it. Okay, and what I just said, here's your vector v in ij form. And this is vector W, and we're just adding component by components. And if we use the Kronecker vectors, the unit vectors, with I and j, we've got 5i and negative 1j. If we're doing it in the form of position vectors, we get an equivalent result. So these results are completely equivalent. And we're going to have to be able to pass back and forth between the two. Second example is subtraction. I'll leave that to you. As you can see, it's worked out in the two different forms. Okay? Okay, scalar multiplication and magnitudes of vectors. All right, so again, we're going to take, this is vector v, this is vector w. Here it's written in terms of unit vectors I and j. Here they're written in terms of position vectors. And we're asked to do a couple things. Now, most of the stuff you can probably do mentally. So 3v, clearly it's going to be 6i plus 9j. And you can do the same type of computation. 2v would be 4i plus 6j. You can figure out what is negative 3w. It would be negative 9i plus 12j. Do the computation. This basically, the magnitude is the length of a vector. It's going to be, we're working with the Pythagorean theorem. Okay, so these are worked out. And these double vertical bars here, that's indicate the magnitude or the length of the vector. And we've used this many times. We've used it in polar. We've used it in de Moivre's theorem. It's the same type of thing. Okay, so work these examples and take a look at them. Let me know if I made any typos. I tried to do it the same way it's done in the book. In fact, I used examples from the book. And, just take a look at the book and work through these. Let me know if I made any mistakes. Okay, we next come to a very important idea, the idea of a unit vector in the direction of a given vector v. Okay, given any non-zero vector v, notice this is in boldface, the unit vector has the same direction as v. So here we go. We take a vector v, which may not have length 1, and we divide it by, this is a scalar now, we divide it by its length. So all that's going to do is it's going to shrink it down, but since we're just dividing by a scalar, it's not going to change its direction. So whenever you want a unit vector, in other words, a vector of length 1, and it's parallel, the same direction as a given vector, this is the computation that you do. Okay, very simple. Okay, so let's do an example. Find a unit vector in the same direction as vector v. Okay, so first of all, we find the length of vector v, which is, the magnitude. Length means magnitude here. And we divide vector v component by components. We divide this part of it and this part of it by the length. And if you want to do a check, you can. Okay, so you can probably do this mentally, right? 4 squared plus negative 3 squared, right? 16 plus 9 under radical 25 is 5. So it looks like this thing has a length of 5. So what we're going to do then is we're going to divide each of the components by 5. There we go, step 1. Here's the computation which we did mentally. You do it out. And here's vector v, and we're dividing each component by 5. So here's what we get. So this is the unit vector that we're looking for in the same direction as vector v. It's just this has a length of 1. That's why it's called a unit vector. Now, if you want to, you can check that this thing has a length of 1. Okay, and it's very easy to do. You just take the vector and you use the Pythagorean theorem and you work this out. And you can see it has a length of 1. And you're probably wondering, well, how do you know, though, that the angle, that the direction hasn't changed? Well, that's easy. This is a vector. Okay, it has a direction. And this is a scalar, meaning it doesn't. We're just dividing by 5, so the direction is not changing. Okay, so moving along. Finding a vector from its direction and magnitude. Okay, here's the magnitude, okay, and cosine theta I plus sine theta j. This gives us the direction. We've seen this type of thing many, many times in the past, okay. Here's your unit vector, okay. And if you want a vector in the magnitude v, it's just a simple scalar multiplication. And we're going to see this type of thing again later. Now, don't be confused. I is not the square root of negative 1. This is a different context. I is the unit vector, the unit Kronecker vector in the x direction. J is the unit vector in the vertical or in the y direction. Okay? So I think what we're going to do at this point is we're going to stop and we're going to then look at some applications. So I'll give you a chance to go back and work the problems, and then we're going to look at some applications. All right, so we'll be back in a jiffy. And of course, this is key to Vector Operations 1, the PDF file, where all of these images are on that. 4 to a page. You can expand it, you can look at it, you can write on it, just to make it a little bit easier for you to follow along. Okay, see you in the next video.